Here is a shape that keeps 1,000 numbers in order. And it still finds any one of them in a handful of steps. Watch it build itself. One rule assembles this entire tree. Smaller goes left. Bigger goes right. That is the whole rule. And that single rule is why searching this tree is O of log n. Every step throws away half of what is left, just like binary search, only now it is a tree. This is a binary search tree. Let me show you exactly how it works, visually. One quick, honest note before we dig in. Everything in this video is free, no wall, no catch. This exact visual style is the whole idea behind my book. Algorithms and data structures, visually explained. 23 of them, each with a clean diagram and runnable Python. $24, link below. Totally optional. The full explainer is right here. Now, let us grow a tree. Let us build the tree one number at a time, and watch the rule do all the work. We will insert 7 values, in this order. 50, 30, 70, 20, 40, 60, and 80. The first value, 50, has nowhere to go. It becomes the root, the top of the tree. Next, 30. We start at the root and compare. 30 is smaller than 50, so it goes left. That spot is empty, so 30 lands there. Now 70. Compare at the root. 70 is bigger than 50, so it goes right and settles in. 20 comes next. Smaller than 50, go left to 30. Smaller than 32, so go left again. 20 lands below 30. 40. Smaller than 50, go left to 30. But 40 is bigger than 30, so this time we go right. 40 settles there. 60. Bigger than 50, go right to 70. 60 is smaller than 70, so go left. It lands. And 80. Bigger than 50, bigger than 70, right, then right again. Look at what the rule built. Every node obeys one promise. Everything in its left subtree is smaller. Everything in its right subtree is bigger. That promise is the whole data structure. Now the payoff. Searching. Let us find 40. We do not scan every node. We start at the root and let the rule guide us. At 50. 40 is smaller, so we go left, and ignore the entire right half of the tree in one move. At 30. 40 is bigger, so we go right. And there it is. 40. Found in 3 comparisons. This is the same idea as binary search on a sorted array. Every comparison cuts the remaining tree roughly in half. Halve. That is O of log n. 1,000,000 values in a balanced tree. About 20 steps to reach any one of them. The tree does the halving for you, structurally, by its very shape. Inserting and searching are easy. Deleting is where people trip, so let us be careful. There are 3 cases. Case 1, the easy one. The node is a leaf, no children. You just remove it. 20 is a leaf. Delete it, and it is simply gone. Case 2. The node has one child. You splice the child up into its place, like pulling a link out of a chain. The child takes over the spot. Case 3 is the tricky one, a node with 2 children. You cannot just remove it, because 2 subtrees need a parent. So we replace it with its in-order successor. The in-order successor is the smallest value in the right subtree. Watch. Let us delete the root, 50. Go right once, to 70. Then keep going left as far as you can. That lands on 60. 60 is the successor. We copy 60 up into the root, replacing 50. Then we delete the old 60, which was an easy leaf. Done. Check the result. 60 is the new root. Everything on the left is still smaller, everything on the right still bigger. The promise held. Now the catch, the thing that can wreck all of this. The tree is fast only when it is bushy and balanced. But look what happens if we insert already sorted data. 10, 20, 30, 40, 50. 10 is the root. 20 is bigger, so it goes right. 30 is bigger, right again. 40, right. 50, right. Every value goes right. The tree never branches. It collapses into a straight line, a linked list wearing a tree costume. Now searching is walking every node, one by one. That is O of n. The log n magic is gone. This is why real databases never use a plain binary search tree. They use self-balancing trees, which rearrange themselves as you insert to stay short and bushy. You will hear their names. AVL trees. Red-black trees. And B trees, the ones that actually power database indexes. We are not implementing them today, just know they exist, and they exist precisely to kill this problem. So why do databases love these trees so much? One word. Order. A hash table, from the last video, is brilliant at one thing, finding a single exact key in O of 1. But its keys are scattered into random buckets. Ask a hash table for every value between 35 and 65, and it has nothing. It has to check everything. A binary search tree keeps its keys in sorted order, structurally. So a range query is cheap. Walk to the low end, then stroll rightward through the tree until you pass the high end. All the values in between, in order, for free. And an in-order traversal, left, node, right, spits every key out perfectly sorted, without ever calling a sort function. That is the honest trade. Hash tables win at single lookups. Trees win when order matters, ranges, sorting, and next and previous. That is why a database index is a tree. Here it is in real Python, and it is shorter than you expect. A node is tiny. It holds a value, a left child, and a right child. Both children start empty. Insert is the rule, written as recursion. If the spot is empty, we make a new node right there. If the value is smaller than this node, we insert into the left child. Otherwise, into the right. Search is the same walk. Empty tree, or a match, we are done. Smaller, go left. Bigger, go right. Read it out loud and it is just the rule, one more time. That recursion is the tree teaching you about itself. Smaller left, bigger right, all the way down. Let us lock it in. A binary search tree follows one rule. Smaller goes left, bigger goes right. That rule keeps every left subtree smaller and every right subtree bigger. So search, insert, and delete all walk down the tree, having the work each step, O of log n when the tree is balanced. Deleting a node with two children means replacing it with its in-order successor, the smallest value on its right. But feed it sorted data with no balancing, and it degenerates into a linked list. Back to O of n, real systems use self-balancing trees, like red-black and B trees, to prevent that. And the reason databases reach for trees over hash tables is order. Sorted keys make range queries and in-order traversal cheap. That is the whole idea. So that is the binary search tree. One rule, smaller left, bigger right, that keeps data sorted and fast to search, and the reason a database index is a tree. We have been building the toolbox. Big O, binary search, sorting, recursion, hash tables, and now trees. Next, we put them to work. Because the next video is where trees and graphs stop being diagrams and start chasing you. A star pathfinding, the search almost every game uses to hunt the player through a maze. It is trees and graphs, weaponized. That is where we go next. And if you want the whole picture, 23 algorithms, each with a diagram and clean Python. My book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.